Assalamualaikum and a very good day to whoever is watching this. I welcome Dr. Wan Faida to watch this video from our group. We are from group 4C, and today we will be presenting our assignment on the retaining structure for the BQS 552 construction technology for course. Today's presentation, we will cover the two case study that we did for the written report, where the case study will analyze the construction methods, materials, machineries, testing, costs, and key challenges involved in the construction or the case study. Without further ado, let's get straight into the retaining structures case study. So for our first case study, it focuses on a completed retaining wall project carried out in Tok Alang, Seberang Perai Utara, Pulau Pinang. The project involved extensive earthworks and also involving the construction of reinforced concrete retaining walls to prepare the site for a housing development consisting of a 95 single-story low-cost house. Moving on to the project background, this project was undertaken to prepare the site for a housing development consisting of 95 units of single-story low-cost houses, together with supporting infrastructure. It is located at Lot 130, Mukim 13, Tok Alang, Seberang Perai, Utara, Pulau Pinang. Before any building construction could begin, major earthworks and infrastructure work were completed, including piling, reinforced concrete retaining walls, drainage system, outfall structures, and road resurfacing. Among these works, the retaining wall was the most critical component because it stabilized the slope, reduced soil erosion, and create a safe and level platform for future construction of this case study. For the next part, let's move on to the parties involved for this case study. Several professional parties work together to ensure that the project is successful to construction, especially PERDA or Lembaga Kemajuan Wilayah Pulau Pinang. They act as a client and funding body which oversees the project's objective. The consultant team include Cityscape Architect as their architect, Perlunding Kejuruteraan MPA as the civil and structural engineer, Sejati Engineers as mechanical and electrical services, and JUB Utara as the quantity surveyor responsible for cost planning, tender documentation, and contract administration. Finally, the contractor carried out all the construction works, including earthworks, retaining walls, drainage, and infrastructure works. Good coordination among these parties ensured that the project met the required quality and design standard that is set. Moving on to the next slide, which is the construction sequence. The retaining wall was constructed in 5 main stages. First, the site was cleared and earthworks were carried out to achieve the required formation levels. Next, the foundation was excavated and compacted before reinforcement bar and formwork were installed. Concrete was then poured to construct the wall stem and base, followed by proper curing to achieve the required strength. After that, a drainage system consisting of drainage pipes, filter materials, and granular backfill was installed behind the wall to prevent hydrostatic pressure. Finally, the wall was backfilled with layers, compacted, and the site was graded to prepare for the next stage of construction. Next, let's talk about the plant and machineries used for this case study. Various construction plants and machinery were used throughout the project. This is done to improve productivity and construction quality of the project. Hydraulic excavators were used for bulk excavation, trenching, and foundation preparation, while dump trucks transported excavated soil and construction materials around the site. Backhoe loaders assisted with the smaller excavation and backfilling works where access was limited. During concreting, ready-mix concrete was delivered by mixing trucks, and concrete vibrators ensured proper compaction to prevent honeycombing. In addition to that, survey equipment such as total station and leveling instruments was used to achieve accurate setting out and retaining wall alignment. Several important materials were used to ensure that the retaining wall achieved the required strength and durability. Reinforced concrete served as the main structural material because it has high compressive strength and can resist earth lateral pressure. Next is steel reinforcement was embedded within the concrete to improve tensile strength, while formwork was used to shape the wall during casting. Granular backfilling, drainage aggregates, geotextile filters, and perforated drainage pipes were installed behind the wall to improve drainage and reduce hydrostatic pressure. Together, these materials combined contributed to the wall long-term stability and overall performance.
Hi, my name is Nooratan, and I'll be continuing with the 3-phase testing framework. In the pre-construction, soil investigation and field density test identified soil properties to ensure a perfectly compacted foundation, while surveys checked verified precise coordinates and alignment. During the construction, we performed slump tests upon delivery to ensure ideal workability, followed by cube compression tests, crush at 7 and 28 days to verify structural design compliance. As the post-construction, we ran drainage inspection on all weep holes and subsurface pipes to safely release hydrostatic pressure, which can lead to retaining wall failures. Next is the effectiveness of the method. The reinforced concrete method successfully delivered on all structural and slope stability objectives through 4 pillars. The first is height structural resistance. The combination of high tensile rebar and compacted concrete easily holds back heavy lateral earth pressure. Second, by dimensional accuracy, advanced survey equipment eliminated foundation depth and alignment errors during the excavation. Next is hydrostatic mitigation. The integrated drainage system prevents groundwater accumulation behind the stem wall. And the last one is settlement prevention. Layered backfill compaction neutralizes future ground shifting, securing a stable graded site for subsequent housing phases. Moving on to the cost involvement. Looking at the financial, the total cost stated on the BQ for this element is 340,780 ringgit and 80 cents only, covering everything from excavation to drainage, but excluding setting out. Breaking this down, the primary cost is steel reinforcement, which accounts for over 50% of the budget at 180,240 ringgit and 20 cents. In fact, the 25 mm height tensile bar alone costs 97,340 ringgit. This heavy investment is critical, since the wall's structural tensile strength relies entirely on this specification. The remaining budget comprises concrete works at roughly 70,500, ancillary drainage work at 65,800, and temporary sound form work at 38,824 ringgit. Lastly, its problem occurred and the solution. We successfully mitigate three distinct site challenges. The first is block access road due to illegal squatters. We issued a variation order for an alternative heavy machinery route and initiate formal relocation procedures with local authorities. The second problem is unmapped water pipeline discovered right under the wall footprint. We issued a VO to relocate the pipeline and resequence our master program to excavate unaffected area first. And the last problem is soil settlement where ground levels drop below design specification. We executed additional earth filling and layered compaction utilizing geotextile membranes in the worst heat zone to guarantee long-term stability.
Assalamualaikum, my name is Muhammad Iman and today I will be talking about our case study number 2, which is an ongoing project. The project title is Cadangan Membina One Block Service Apartment, 27th floor. It located at Hulu Kinta, Perak Darul Rizwan. For our project background, the project title is Cadangan Membina One Block Service Apartment 27 tingkat. The project location is located at Lot 535822, Lebuh Bercang Selatan, Medan Bercang Selatan, Bercang Mungkin Hulu Kinta, Daerah Kinta, Perak Darul Rizwan. Our project overview is the construction of a 27-story service apartment consisting of 394 residential unit. The unit composition is we have 200 type A service apartment, 186 type B service apartment, 4 type of duplex loft unit, 4 type B duplex loft unit, and we also have a supporting facility which include a swimming pool, gymnasium, roof garden, community hall, management office, guardhouse, refuse chamber, 2-story commercial building, 4-story car park, and a TNB electrical substation. For our parties involved, the project owner for this project is Lux Premier Group Sdn Bhd. For the main contractor for this project is Bex Construction Sdn Bhd, which manage the construction work, labour, material, subcon and site activities. It is to ensure the project is completed safely, on time and to require the quality requested by the client. For the consultant team, we have the architect, which is a BKOOI architect. It has prepared building design and drawing. They coordinate with the consultant to obtain the approval and supervise the construction. For quantity surveyor, we have a HQS Consult. This company help prepare cost estimate and bill of quantities and manage the project cost variation and contract administration. Next, for the civil and structural engineer, we have AJL Perunding. This company do the design structural component and ensure the building is safe, stable and complies with the engineering standards. For our M&E engineer, we have Mokhtar Consult and Associate. They have designed the M&E services, which include electrical, plumbing, air conditioning and fire protection. They ensure the building service function effectively and comply with the regulation provided. And lastly, we have a landscape architect, which is a Prima Collaboration Sdn Bhd. They do the design for our external landscape, softscape and hardscape, and they also help improve the aesthetic and functionality and improve environmental quality. For the construction method, firstly we must do is the site investigation and setting out. This is to conduct, we need to conduct a site investigation and a survey work to determine the soil condition, wall alignment and foundation level before the construction begins. After that, we need to do a site preparation and do an excavation. For this, we need to clear the site, prepare the temporary facilities and excavate according to the design while ensuring the safe working environment. After we done that, we go to the foundation preparation. Compact the subgrade and construct the reinforced concrete foundation to provide the stable support for the precast retaining walls. After we have done the foundation preparation, we go to the drainage system installation. We install a drainage pipe, granular backfill and geotextile fabric and whip hole to reduce hydrostatic pressure behind the wall. After that, we wait for the delivery and installation of the precast wall unit. The transport of precast panel to the site, inspect their condition and install them using a mobile crane while checking the alignment and stability. After all of that, we must do a joint treatment and backfill. We need to seal the joint, secure all the connection and carry out a layer backfill with a proper compaction until the final ground level is achieved. For our plant and machinery used in this retaining structure construction, first we have an excavator. It was used for site clearing, excavation and backfilling, and also remove an unsuitable soil with a careful excavation around the existing underground drainage system. Next, we have a mobile crane. This helps lift and position the precast retaining wall panels safely and accurately onto the prepared foundation. After that, we have a dump truck. This is used to transport the excavated soil away from the site and deliver a granular backfill material for this construction. We also have a compaction equipment. It helps compact the foundation and backfill to improve the soil stability and minimize future settlement. And lastly, we have a surveying equipment. This is used to total the station, laser level and spirit level to ensure the accurate alignment, level and positioning of the retaining walls. Next, we have the material used in retaining structure construction. Firstly, we have a precast reinforced concrete wall panel. It is a factory-produced panel that provides a high strength, consistent quality and accurate design. We also have a reinforced concrete foundation. This is used to support the retaining walls and transfer their structural loads safely to the ground. We also use a granular backfill material. This is for a free draining material placed behind the wall to reduce earth pressure and improve our drainage. We also have a drainage pipe and geotextile fabric. This perforated pipe remove the groundwater, while the geotextile fabric prevent the soil from clogging the drainage system. Lastly, we have a grout and joint sealant. This is used to fill the panel joint, improve a structural continuity and prevent water penetration. That's all.
My name is Ala Shamina bin Rahimi, and now I will be explaining the next critical component in this case study number 2, which is the testing. Several testing processes are essential across all project phases to ensure that materials, workmanship, and final design consistently meet structural stability and quality standards. As you can see on this slide, we break this down into two main categories. First, on top, during the pre-construction and construction phase. Soil investigation conduct during the pre-construction phase, which determines the soil bearing capacity, which allows us to identify the appropriate construction methodology. Next is the concrete slump test, which is conducted immediately upon fresh concrete delivery to verify workability and mixture ratios before pouring. And the next is the concrete cube compression test, where the concrete samples are cast on site and water cured for 7 to 28 days, then mechanically crushed to verify that the structural strength complies with our requirements. Next, as you can see on the below, for post-construction validation, which is survey and alignment checking, this step validates geometric precisions, ensuring dimensions, horizontal location, level and vertical alignment all match project specifications. And then lastly, the drainage inspection. Finally, we will inspect the whip hole and drainage pipes to ensure water management systems are installed correctly to relieve hydrostatic pressure behind the wall. Now, let's discuss the effectiveness of this method used for this retaining wall construction. Overall, this construction method is highly effective in ensuring structural stability and preventing soil erosion along the area. The process follows a schematic sequence, which includes site clearing, excavation, followed by foundation construction, reinforcement installation, formwork erection, concrete casting, curing, masonry and plastering works, and finally cover installation to proceed with the backfilling. So this method offers several key advantages, as you can see on the slide. Firstly is the lateral resistance. It provides adequate resistance against the lateral earth pressure. Next is the slope stability. It improves the slope stability and minimize the risk of soil movement. Thirdly, it enhances the safety, which improve the site safety both during and after the construction process. And then increase durability. It enhances the service life and durability of the retaining wall structure. Lastly, help contribute in the water management. It facilitates proper drainage to reduce hydrostatic pressure behind the wall. Now, let's move on to the next slide, which is the cost involved. For the case study number 2, the total construction cost for the project is RM194,642.94. The project encompasses the following scope of work, as you can see on the slide: excavation, site preparation and foundation construction, installation of steel reinforcement, formwork erection, and concrete casting. Next, the curing, masonry works, plastering, and cover installation for backfilling. This scope of work inclusion of all labour, construction equipment, material, and transportation costs. Next, as you can see on the bottom of the slide, the major cost contribution for this project are identified as follows. As you can see, the excavation works, the foundation works, the reinforced concrete wall, and additional components, which account for the capping beam, formwork, and reinforcement, as well as brickwork and whip hole installation. Now, let's move on to the next slide, which we will discuss the problems occurred and solution in this case study number 2. So the first problem is the extension of time due to defective retaining wall construction problem. So the retaining wall had structural defects that did not meet the approved design or technical requirements. So the correction process necessitated extra time for investigation, repairs, and securing the necessary approvals. So these delays caused an EOT and disrupted the overall project schedule. So the first solution is to strengthen the quality control and site supervision. Next is to perform material and structural testing before proceeding to subsequent works. And then lastly, to improve communication between the contractor, consultant, and the supervising engineer to resolve this issue promptly. Next, we move on to the next problem, which is the reconstruction due to failure to meet the authority requirements. So this problem basically, after the inspection by the authority, the portions of the retaining wall failed to satisfy the required standards and specification. So this resulted in the non-compliant section being demolished and to be reconstructed, which led to additional costs and the project might delay. So the first solution is to obtain approval for shop drawings and construction methods prior to execution. Next is to carry out the regular inspection jointly with the consultant and authority representative. Thirdly, to ensure construction personnel fully understand the project specifications and regulatory requirements. And the next is to implement a comprehensive quality assurance, quality control, QAQC, system to detect and rectify non-conformance at an early stage. And then next, we will see the last problem occurred in this project, which is the retaining wall work disrupted by the underground drainage. So the problem is an unexpected 600 mm underground drain was discovered during the construction, which had not been identified during the planning stage. So the foundation work had to be halted while awaiting a decision from the consultant on whether to move or remove the drain, so resulting in project delays, extra costs, and a disrupted schedule. So the solution is the engineer must check all existing services and as-built drawings during the planning stage to identify potential conflicts. Next is to hold a meeting with the client, consultants, and utility authorities before starting construction to ensure proper communication. And then lastly, if underground services are found, consultants must revise designs and obtain the approval before work is proceeded. Thank you.
Now we will look at what are the differences between case study 1 and case study 2. The first case study being a public sector community development project that has been funded by the Penang Regional Development Authority, which is PERDA. It involves extensive amount of earthworks and preparation for infrastructure works for a horizontal housing scheme that has 195 low-cost single-story houses that is located in Seberang Perai Utama, Pulau Pinang. In contrast of case study 1, case study 2 is a high-density vertical mixed-use private development by the Lux Premier Group's SDM-BHD that is located in Bercham, Perak. It is a big project that features a 27-story service apartment tower with 394 housing units, a commercial building, a multi-story car park, and also area for recreational amenities. For the structural part, case study 1 depends solely on the traditional reinforced concrete cantilever retaining wall system. This structure has a base slab that is quite thick and vertical stem that is designed to influence the heavy backfill soil weight that is resting on the base so that it resist the lateral pressure of the earth, including sliding and overturning. For case study 2, uses a hybrid retaining methodology that consists of reinforced concrete retaining wall for a deeper trench zones that is up to 4 meters and a brick retaining wall system that is topped with a concrete capping beam for the trench that is a bit shallower, which sections up to 1 to 2 meters in height. These two materials choices makes case study 2 able to optimize costs by using rigid reinforced concrete only to area where the lateral soil pressures are the highest, and using the localized brickwork for ground stabilization with lighter needs. Next, for case study 1, it is fully built on site using ready mixed concrete trunks, sun formwork panels, and concrete vibrators to pour the stem and the base. As for the second case study, it uses more towards industrialized building systems, which also known as IBS, that utilize factory manufactured precast reinforced concrete wall panels that has been transported to the site. Once it gets on the site, it got erected by using mobile cranes. Moving on next to what challenges did case study 1 and case study 2 went through throughout the project. Case study 1 faced a very risky problem during a preliminary phase, which is restrictions in accessing the site due to existing squatter houses. This problem required a neatly and strategic clearance and social management before safely transferring the heavy plants and machineries into the work zones. Case study 2 also went through some problem, which is in the form of operational and regulatory failures, and that severely messed up the construction schedule. The project has encountered a problem when the returning wall developed structural deficiencies and non-conformance that messed up with the approved design by the engineer and the requirements of the local authorities. These failures has forced the contractor to pause the work, executed a partial demolition, forcing the contractor to reconstruct the sections that are non-compliant to the engineer and the local authorities. Now, it has been analysed that both of the sites uses similar technique sequence for earth retention, which sequence as setting up, site clearance, deep trench excavation, foundation preparation, subgrade compaction, drainage management, and also progressive backfilling. Both projects also use similar machineries, which relies heavily on hydraulic excavators for any bulk excavation, transporting materials using dump trucks, and eliminate soil voids during backfilling by using a specialized vibratory equipment. In conclusion, this research and the analysis that have been conducted across both of the case studies indicates that the selection, design, and execution of earth retaining structures are vital in order for the project to succeed, while also giving it structural safety. While the core engineering principles remain the same, which is withstanding the lateral pressure of the earth while also preventing catastrophic slope or any soil failures. The structural approach would need to adapt to the specific scale, funding sector, and boundaries of the project. In this report, case study 1 has successfully highlighted traditional application, which is the cast in situ reinforced concrete cantilever walls for the low-density housing developments. From this, we found that maximizing the self-weight of the backfill soil over a substantial base slab is way more effective for a broad slope. Other than that, case study 2 shows a more complex footprint. It shows that by implementing a hybrid approach, we can achieve structural stability by utilizing rigid reinforced concrete for excavation in deep trenches, and also localized brick retaining walls with concrete capping beams for shallower excavation sections. Ultimately, the challenges that both projects face, from initial site accessibility issues that has caused by squatters housing in case study 1 to a more major structural deficiencies and non-conformance from case study 2, serves as one of the most important lessons for construction management that have been learned in this case study project.